Okay, so this video is going to take you through a couple of important concepts that lead into some calculations, but those calculations, most of those will be for another video. But what we're going to look at right now is what is known as a rate law or rate law equation. And the other concept we're going to look at is this concept of reaction or an overall reaction order. And so you see how those work. But before we get started, I'll just give you a quick little warning. If you just have a look over here, and you'll see that there is a fair bit of text to be covered here, and I'll cover most of that at the beginning. So as it says, maybe watch and listen first, then you might want to rewatch and make a few notes or jot a few things down. Anyways, that's just a suggestion. So here we go. So rate laws, they're equations that are derived from the fact that changing concentration of reactants will have an effect on a rate of reaction. We know this already as one of the factors that affects rate. So with prior knowledge of a given reaction with respect to all reactants, so this is what's important, prior knowledge with respect to all reactants, one can easily manipulate a reaction to change the rate, either increase it or decrease it. And so that's very important from an industrial point of view, because in the lab, industrial chemists will look at a rate or look at a specific reaction, determine the experimental rate of reaction, and from that they can apply that knowledge to the industrial level and manipulate reactions, either to make them go faster or to hopefully make them yield more product, or whatever the case may be. So the experimentation done in the lab applied on the industrial level. Prior knowledge then comes from a lot of experimentation. This is a very experimentally heavy discipline, reaction kinetics, and once you've determined or a lot of experimentation, you can turn the rate law for that reaction. So rate laws can only be determined experimentally. I keep mentioning that. That's a critical point. This is not something we get from a balanced chemical equation. So let's keep going. So here we have a simplified reaction. So what we're looking at here is J plus K yields products. The lowercase j, lowercase k are meant to represent possible coefficients for those reactants. And so again, the evidence shows that the rate of reaction is going to be proportional to the product of the initial concentration of the reactants, where each concentration is raised to some experimentally determined exponent. So we can write this as a proportionality. So rate R proportional to concentration of J multiplied by product of concentration of K, raised to some experimentally determined exponent. And those exponents can be, well, anything. They're experimentally determined. So the reason I've put A and B here is to drive home the fact that it is not necessarily from a balanced equation. It is not necessarily lowercase j and lowercase k as the exponents to the concentrations. It could be, but it doesn't have to be. Okay, so then if we get a constant of proportionality, which we get again by graphing, you'll see this in a minute, we can then express this as a rate law. And so this becomes an equation. R equals, there's my K, concentration of J raised to some exponent, I'm going to keep that as A, concentration of K raised to some exponent, and I can keep that as B. So what we now have is a proportionality that can be turned into an equation by adding that constant of proportionality. So just a few definitions, a few bits of information you need. Rate law, an expression relating rate of reaction to the concentration of reactants. It's always reactants. We're not concerned about products at this stage. Reaction order is, by definition, the exponent to which a particular reactant concentration is raised in a particular rate law. So that's the exponent. So in our previous example, the reaction order in the reactant J was actually A. Overall reaction order then, the sum of the individual reaction orders, or the exponents in a given rate law. And finally, the rate constant. This is a constant of proportionality, links the reaction rate with the concentration of reagents. Rate constants are specific to a particular reaction. Rate constants are independent of concentration and time. That is, they're constants. But rate constants are dependent on temperature. So rate constants will change if the temperature of a given reaction is changed. And rate constants have complex units. You're going to see more about this in a little bit. Okay, so just a bit of terminology you should be familiar with. All right, so let's just label this rate law equation. So obviously R means rate. So this is our rate constant. Okay, and that's a lowercase k. You're going to see in the next unit that uppercase k means something different. Not a lot different, but it is definitely different. So it's a lowercase k. So what we have here is the concentrations of our reactants. And concentration now is moles per liter. And what we have here is the reaction orders, or exponents. And so we can say reaction orders in a certain reactant. So what we have here is reaction orders in A and B. So the reaction order in A is lowercase a, etc. All right, so that's what a typical rate law equation looks like. All right, now I want to consider this simple generic reactions. We have 2A plus 2B plus C yields products. So we have some experimental evidence about this reaction then. The reaction involving these reactants is said to be first order in A, second order in B, and zero order in C. You'll see what zero order means in a minute, but what is the rate law for this reaction, and what is the overall reaction order for this reaction? So it's important to realize if you have information about reaction order in each reactant, you can write a rate law directly. This is the experimentally determined evidence we need. So the experimentation gives us the reaction orders. Once we know the reaction orders, we can write a rate law. So again, it's the generic R equals K, A, B, C, and now we raise them to the exponents given to us by the reaction order. So first order in A, so that's a 1. Second order in B, that's squared. Zero order in C, that's a 0. Now, there's another way to write that, and it's a little simpler, and it should make sense to you. R equals K. So concentration A, well, raise anything to the power of 1, and what do you get? You get the same thing. So concentration of A will not change when it's raised to the power of 1. Concentration of B will change when it's raised to the power of 2, so we leave it that. And think about this. Concentration of anything raised to the 0. Well, anything raised to the 0 is 1, and so that's like multiplying by 1, and so we don't bother. We just leave that out. So C will not affect the rate of reaction, and so that's important to realize. So there is the reaction rate law expression, and in terms of reaction order, overall order is the sum of the exponents, and so the sum of the exponents is 3. So overall order is third order. Now, so that becomes a useful tip. If you know the reaction order of reactants, you can write a rate law directly for that specific reaction, and you can determine the overall reaction order. So that becomes useful at times. Another way to recognize orders of reaction is from graphs. So straight line relationships, we see a lot of straight line relationships in science, and that's for a reason. If we have a straight line relationship, we can determine that constant of proportionality, and hence that's in reality is the slope of the line. And so in reaction kinetics, we plot experimental data, try to get a straight line, and when we do, we see a type of reaction order. So we have 2 showing here. We've already seen both of these in number only. This is 0th order. 0. And so basically what that line shows is it doesn't matter what you do to concentration of J. Initial concentration of J, you're changing, increasing. This is the rate. The rate does not change. So 0 order reaction, the rate of reaction is independent of the concentration of J. You can raise it to whatever amount you want. The rate of reaction does not change. This one is first order. So that's that exponent 1. And again, you can see from the graph, it's a straight line relationship. And if I have initial concentration there at one point, and if I double it, so now that's a doubling, you can see the rate doubles. So that first order reactions are quite common, and basically what you see then is a doubling of a concentration yields a doubling in rate. One more to look at. Now this is a curve that gets generated quite a lot, and it's actually a second order reaction. So exponent is 2. Now we can't get a constant of proportionality from that curved line. So what if we graphed concentration of J squared? Well, lo and behold, we get a straight line, and so that's how we generate our constant of proportionality. And essentially, again, what it says is, as you raise the concentration of J to the second power, you end up getting a doubling of rate, and so that's a pretty common reaction order as well, second order. And so that's a useful tip, because you can recognize the order of reaction from these graphs, first to second, first zero order, first order, second order, from the graphs. If you have the graphs and you can recognize the order, you could write a rate law equation. All right, a couple more examples before we finish up. So an experiment carried out for a reaction. So this is the important bit. An experiment is carried out. So what we now have is experimental evidence that's going to help us determine our rate laws. And so in this particular reaction, the reaction is first order in hydrogen chromate ion, first order in hydrogen sulfite ion, and second order in hydrogen ion. So we have the information we need to write a rate law. So answer to the first question, A, determine the experimentally derived rate law. Well, that's going to be R equals K, hydrogen chromate ion, first order, so raised to the power of 1, hydrogen sulfite ion, first order, and hydrogen ion, second order. So there's my experimentally derived rate law. What is the overall reaction order? Remember, overall order, sum of the reaction orders of the reactants. So that's going to be 1 plus 1 plus 2. So this is a fourth order reaction. First order in hydrogen chromate, first order in hydrogen sulfite, second order in hydrogen ion, fourth order overall. Now, let's carry on with this one. Now we have an initial rate of reaction, 3.2 times 10 to the minus 3 moles per liter second. So if the initial concentration is such, that's when we can calculate that rate. We have to know the rate constant, but we do know that that's the rate for those concentrations. So if you double the rate of hydrogen ion, what happens to the rate? Well, if you double, so here what we have is rate proportional to hydrogen ion raised to some order, and that order is 2. So we've doubled concentration raised to the order 2. So rate is going to increase by a factor of 4. And so rate's going to be 3.2 times 10 to the minus 3 moles per liter second times 4, or it's going to be 1.8 times 1.28 times 10 to the minus 2. So 1.3 times 10 to the minus 2 moles per liter second, if I've done my math correctly. Anyway, the point being, you can look at how the effect of a single reactant, like hydrogen ion, which is raised to this order, how that will affect the rate of the reaction. You can look at that independently of any other reactant. Now, how about determining the value of the rate constant? This is pretty important because we do have to look at the units here. This is where units become important. So let's look at the rate constant. So if you remember, our rate equation is R equals K chromate, hydrogen sulfite, hydrogen ion squared. And so what we're looking for is K. So we can isolate K. K equals R over all of these ions. And it's still a concentration. And we have all that information, so it's simply a case of plug and play. And and generating our number, and more importantly, generating the unit. This is where you need to realize what the unit looks like. So we just look at information we're given. So we're given an initial concentration, or sorry, initial rate of 3.2 times 10 minus 3 moles per liter second. Initial concentration of hydrogen chromate ion was 0.1 mole per liter. Initial concentration of hydrogen sulfide ion was 0.1 moles per liter. And the initial concentration of hydrogen ion was 0.2 moles per liter. And then we square that. So the number is easy. We just do a calculation and we get this number, 8.0 times 10. Oops, it's just 8.0. We just get 8.0. Now the unit is what's important. Now I'm going to do the unit analysis off to the side here. So what we have is moles per liter second divided by, if you look at all of these units, moles per liter times moles per liter squared becomes moles to the fourth liters to the fourth. Well, that's the same as multiplying by moles per liter second times liters to the fourth moles to the fourth. I've just taken the reciprocal of this to get it up above. So what I get is I lose one of those and I have moles to the third in my denominator. I lose a liter and I have liters cubed in the numerator, and so my unit becomes liters cubed per mole cubed second. Okay, so the unit for the rate constant is important, because other questions you will be asked is, now that you know the rate constant, determine the rate of reaction at a given time or with a given concentration. So the unit has to be correct. You always generate the unit for concentration. Remember, the unit for concentration, or sorry, unit for rate is always moles per liter second. Rate unit, always. All right. So summary. A few things. Reactions at a specific rate law. Reactions have a specific rate law that relates rate to concentration of reactants. Reactants have a specific reaction order, which can only be determined by experimentation. Reactions have an overall reaction order, which is the sum of the reaction orders of all reactants. And reactions have temperature-dependent rate constants that can only be determined by experimentation, and that have somewhat complicated units. So again, I reiterate, it is important you do the unit analysis for your rate constant carefully. And that concludes this video.